Okay, welcome back to your Torsion Module 3. So we will now proceed with your Unit 2, which is the flanged bolt couplings. So in this unit, we are going to derive the formula of the torque capacity of the flanged bolt couplings, and then of course to solve problems regarding this and with the multiple concentric port circles. Okay, so we will discuss that one. So if you say flanged bolt couplings, or if you say couplings, okay, you can read about that here. But that simply means that we are going to connect two members or shaft that is handling a torque, okay? And then how to connect that one using, of course, the both ends. There are ways to connect that one, but most of the time we are connecting that one using a flanged bolt. Okay, if you say flange, that is this part. Okay, let's consider this as this right side as another member, and the left side is another member. Okay, so this left side. This flange here, the circular shape object here is the flange, and of course the circular here is the flange of the other side. And then these are the end of these members. We are going to connect those using the bolt. Okay, and this connection flange with the bolt, we call that one a coupling. So that is a flange bolt couplings. Because there are other connections, you can actually connect this one by means, if this is steel, this is a metal, you can actually connect that one by means of welding. But of course, most of the time we are using a bolt. Why? Because you can actually detach that one. But if that is a wheel, then that might, you can detach, actually you can remove, but that will give you hard time separating these two flanges. Okay, so flange bolt couplings, it is the connection of a two member, okay, in this manner. And in most of the cases, this is how we will try to connect these two flanges by means of bolt. And of course, most of the time we are using circular. Okay, we are arranging these bolts in circular manner, and actually that is the best way to arrange that one. Okay, again, as you know that, isn't it? These members are carrying couples, or what we call this one, torques. So it is always best for us to maximize where we will put these bolts, because the farther the bolt, okay, the farther the bolt from the center, the bigger. Since again, that is more stress. The farther the point from the center, that is more stress. So the farther the point where we will put the bolt, the bigger it will handle from the torque. Okay, the bigger it will handle of that torque. Okay, so that is our manner of joining these flange bolt couplings. So commonly used connection between two shafts is a flange bolt couplings. It consists of flange rigidly attached to the ends and so on and so forth, bolted together. The torque is transmitted by the shearing force P created in the bolts. Okay, so as you can see here, for us to analyze these bolts, since actually that is our main purpose here, the connection, okay, of these two flange, which are the couplings. Okay, we are going to analyze the stress on the bolts. That is our main point here, not on the member, because we are done with that. If that is circular, then that is just like our unit 1. Okay, so our main purpose in this unit is to analyze the connection, this connection. We will focus in this connection. So we are going to distribute this torque, okay, into each of these bolts, and that equivalent force handled by by each of these bolts is the force P, okay, which is of course a part of this torque. Okay, this torque will be distributed in each of the bolt, which will be in a force P. Okay, so assuming that the stress is uniform distributed, the load in any bolt is given in the simple set. What do we mean by uniformly distributed? That doesn't mean that from this point outwards is uniform, because I've explained before, a torque, okay, torque is a variable stress. What do we mean by that, uniform distributed, is that let's assume that this torque is being handled by these bolts equally. That is the meaning of that. Okay, so each of the bolt, okay, will handle a force P, which is equivalent to the area of the bolt. Okay, we discussed about that, about simple shear. Okay, the area of the bolt multiplied to the shearing stress. This is the shearing stress. Whatever stress is transmitted in this bolt, multiplied to the area of that cross section of the bolt, then that is the force P being handled. Okay, so again, that is within the area and the stress or shearing stress. Or again, if we go back, that P there is the V. But actually, as I've said before, it doesn't matter what is that as long as that is the force, okay, creating the stress. But before, we use V for shearing force, okay. And equals pi d squared over 4 pi. So all we need to do is break this down. Your area, what is the area? That is, of course, bolt is a circular shape. So what is the area of a circle? Pi d squared over 4. So we can break this down, okay. Since later on we will be needing the diameter, so we really need to break this down. So it acts through the center of the bolt and tangent to the bolt center, bolt circle, I mean. So what is that bolt circle? Okay, the bolt circle is actually the circular, the imaginary circle created by the designation or the location. Okay, it is the path being followed by the distribution of your bolts. That is the bolt circle that we are talking about. Okay, so therefore, for any number of bolts n, okay, so how many number of bolts are there in the bolt circle? Okay, that is your n. The torque capacity of the couplings is expressed by this one. Okay, so as I've said, the torque is being handled, okay, is being distributed as a force P in each of these bolts. Okay, so we will now try to break this down. Your T will be equal to P times R. What is that PR? That is, the PR is a moment of the force P, of each of the force P on each bolt, multiplied to the radial distance to the center. So that is the a couple, that is already a moment. That P times the R is a moment which is being handled by this bolt. In here, the same. P, we have here another P tangent to that, times the distance, which is radial distance, radius also. So the radius there, the R there, is actually the radius of the bolt circle that we are talking about. Okay, so how much of that? P times R, how much of that? Multiply that one to n. N is, as I've said a while ago, is the number of bolts. So therefore, that should equal your torque in order for that to be handled equally. Because if that is not equal, let's say that P R times N is less than T, then it means that your load, the torque load, is very, very high. Therefore, this will fail. The connection will fail. Okay, the bolt cannot handle that. In case that shearing capacity of each bolt is exceeded, it means that the P that this bolt can handle is already exceeded. Then that means this will fail. Not the flange, but the bolt connecting the flange. Okay, so the coupling, the entire of this is what we call as the coupling, will fail. Okay, so that is the meaning of that. Therefore, for us to equate that T, that should be handled by the P times R times the number of that bolt. Okay. However, as I've said, that PR, okay, that PRN, your P will be changed to A times tau. Okay. Tau is the shearing stress, area times the shearing stress, cross-sectional area of the bolt times the shearing stress of the bolt. But your cross-sectional area will be changed to pi d squared over 4, that is for circle. So your P will be changed to this times tau and then Rn. Okay. So that is our formula for flange bolt couplings. So occasionally a coupling has two concentric rows of bolts. Okay, in case most of the time we are going to what to call this one, arrange this into this manner, the bolts into this manner. You can have more than one bolt circles. Okay, so that is the most scenario. Why? Because sometimes even if you want to maximize all of that bolts on one outer bolt circle, but if I will put there, that is now too close with each other. And what happens if the bolts are too close with each other? The failure will not happen on the bolt, but it will happen on this path. Okay, look at this. If that will turn, okay, if that will turn, and then these two bolts are very close, then this plate or the flange will tear apart. We discussed that one in bearing, isn't it? If the plate cannot handle the bearing, then the plate will tear apart. So that is a tearing failure. Okay, tearing failure. Okay, so that is tearing failure. So that happened because the flange cannot handle the bearing stress. So for us to this one, for us to consider that one safe, okay, from tearing, then we will try to make two circles which have the same center. We call it one concentric circles. So we will try to divide your bolts and then distribute it in two circles. If still that is not enough, they are still too close, then create another one. You will have another third bolt circles. So in case this is what happened, okay, you need to consider this. As I've said, that the stress on a torque is variable. From center outwards is increasing. So whatever stress is experienced by the smaller circle, that is less than compared to the one experienced by the outer circle, since the outer circle is farther from the center compared to the inner circles. So if we are trying to design this one and you are given the capacity of the bolt, okay, you are given the shearing strength of the bolt, of each of the bolt, of course, this will be composed of the same type of material, the same type of bolts, the same size of bolts. But the point there is, do not use the entire, okay, do not use the strength in all of this. You will be using the strength on the outer. The one will be using lesser stress. Why? Because as I've said, the stress on this torque is not uniform. So we will have an example like that later on, so that you will better understand. So what happens there is, isn't it? We discussed about that for one circle, that is PRN. PRN for one circle. Since we have there more than one circle, all we need to do is summate. Whatever is torque handled by that is PRN. Whatever torque is handled by that's also PRN. If we have another, then that is another PRN. So all you need to do is summate all of those PRN, then that should be equal to T. Okay? That subscript will actually means they have different values. They have different P, they have different R, and then they have different numbers. It depends. Okay. So P there is the shearing force handled by each of the bolts, and then R is the radius of the bolt circle. Okay. Most of the time, okay, the big, what to call this one, big, or the capital letters, these are your bolt circles, and in the small letters like the R and D, since we have a radius and diameter of the bolt, we have a radius and diameter of the bolt circle. So the capital letter, that is the bolt circle, the small letters, these are the bolts itself. So N is the number of bolts in the bolt circle, okay, as I've said a while ago. So N1 is for the first, N2 is for the second. So the relationship between P1 and P2 can be determined from the fact that the comparatively rigid flange cause shear, the formation of bolts that are proportional to the radial distance from the shaft axis. Thus, the shearing strains are related by, okay. So therefore, as I've said, since these are the stress is actually proportional to the distance, okay, to the distance, then actually you can apply ratio and proportion on these two bolt circles. So first bolt circles, what is that? Lambda. Lambda is actually, we discussed this one on a simple strain, isn't it? Lambda is the what we call strain. Strain, but that is a shear, because if we are referring to a simple strain, then that is, or normal strain, that is your E, okay, your E. Then this is a shear. We are talking here of shear, so that is shear strain, so that is lambda. Lambda 1, lambda 2. The shear strain in your first bolt, second bolt circles, and then these are proportional to your radius, the distance, the radial distance. Okay. So from this we will now derive, okay, using Hooke's law, okay, your J is the stress over strain, just like E. Okay, E, as I've said before, is normal stress over normal strain. But since we are on modulus of rigidity, that is J, okay, so that is still stress over strain, but we are now referring to shear stress over shear strain. Okay, so your shear stress is tau. Okay, play around with this, look at this, cross multiply, so that your lambda will become tau over G. Okay, so your lambda will become tau over G. You still have there R1. Same thing happens with your second circle here. So if this is the case, then actually I can break down also the tau. The shear stress is force, shear force divided by area. You can break that down also. Same thing here. So that we will now actually try to expand the formula and then look at those that are constant, and we can cancel that out. Okay? Since we are referring here to same material, which is actually the case. Seldom that we will have different materials. But in case there are different types of materials in the bolt, then we cannot cancel out J. So if that is equal, then I can cancel that out. What else? The area, the sizes of the bolt is equal. If that is equal, then area 1, area 2 will cancel out. So we are left with P1 over G1. J and J cancels, A and A cancels. So P1 over R1 will be left. P2 over R2 will be left. Therefore, that is the relationship of the P handled by each of the bolt from their location. So, okay, we have P1 all over its distance R1 is proportional to the ratio of P2 over the radial distance R2. So that is the relationship of the P and their distance, okay, of these different bolt circles. We will be needing this one in case we have more than one bolt circles. Okay, so let's have one. Okay, sorry, this is not supposed to be continued. That is the simply number 1. This is the start of that. So, flanged bolt couplings consist of 10-20 mm diameter bolts spaced evenly around the bolt circle for 100 mm in diameter. So, we have this size, okay, the size of that bolts are 20 mm, then there are 10 of that, so your N is 10. And we have only one bolt circle, one circular arrangement, so that has a diameter of 400, so this is 400. Determine the torque capacity of the coupling if the allowable shearing stress on the bolts is 40 megapascal. So we are now given the strength of each of the bolt in terms of shear, okay, and that is 40 megapascal. So write that down. So your small d, that is the diameter of the bolt, is 20. Number is 10. The big D is the diameter of the bolt circle, which will be needing later on the radius. So 200, or that is 0.2 meter if ever we need the meter. And then the allowable, it means that is the allowable, means that is the strength. So we can reach only up to 40 megapascal on the bolt, so that it will not fade. So solution, the torque, okay, we are finding the that the required here is the capacity, torque capacity. So what is our formula? T is equal to PRN, wherein your P is the area times the tau, but your area is circular, so pi d squared over 4. And then the tau, that is the shear, okay, shear on the bolt. Since we are finding the capacity, so we will maximize the capacity, shearing capacity. So I will input that pi d, your d is 20 mm, that is 4, and then we will maximize this one. I will input the megapascal, so Newton per mm squared, so that should be, everything should be in millimeter. So look at this, why is that is meter? Because look at this. Mm squared cancel, Newton times the meter will give me a Newton meter. But in case I put this one as millimeter, I will have their Newton millimeter. It's okay, you can have that, but you need to transfer that one later on, because that will be a very, very big number. Okay, and as you can see in the answer here, okay, N is 10, okay, your R there, I put there again a 0.2. So that I want to have a Newton meter, because millimeter squared cancels. So I have here 25132.74 Newton meter, or the other equivalent of that, if I want to put that in kilonewton divided by 1000, 25.13 kilonewton meter. So that is the torque that can be handled by this coupling. Okay, this is the coupling. Okay, so that is the torque that can be handled by this coupling. For us not to exceed the maximum capacity of the bolt, which is 40 megapascal. Okay, so as simple as that. So let's have another, but this time we will be having two, okay, bolt circles, so that you will see. So a flanged bolt coupling consists of 8 10 millimeter diameter steel bolts on the bolt circle for 100 millimeter in diameter. So that is the outer, okay, that is the biggest. Okay. You might be asking, why is it that we cannot put that one very near your edge? Because of course, imagine if I will try to approach that edge, then what will fail is not the bolt but the flange, because the covering, or the one that will be holding the bolt, is very thin, so that will snap, the edge will snap. Therefore, there should be a safe distance. Okay, and that will be computed if you will now focus on the strength of the flange. So that is why there is still a space. Okay, so as you can see here, okay, these are your dimension. We have there in the first bolt circle, we have 8 of that 10 mm. Okay, and then on the second bolt circle, we have there 6 of that same size 10 mm. Okay, and then what torque can be applied without exceeding the shearing stress of 60 megapascal in the bolts? So the strength of all the bolts, okay, the maximum strength or shearing strength of that is 60 megapascal. So what torque can be handled by this coupling? That is the question. So you need to have their subscript, since we have there 2 bolt circles. Okay, D1, small d, is the diameter, which is actually the same in D1 and D2. Okay, since we are using the same size. The N, these are different, since in the first bolt circle, the outer, there are 8, and in the second, there are 6. Diameter of the first bolt circle is 400, so radius of that is 200 or 0.2. Diameter of the second bolt circle is 300, and that radius is 150 or 0.15 meter. The allowable stress of each bolt is, shear stress of each bolt is 60 megapascal. That is the strength. Okay, so this is now where we will be applying what I discussed a while ago, that the stress experienced from the center going outwards is variable. Okay, so 2 bolt circles will not be subjected to the allowable shear stress 60 megapascal. Unlike in your example number 1, we will apply the entire 40 in all of the bolts. Since they are on the same circle, so they will experience the same amount of stress. However, in here, yes, the first circle will experience, but the second will not. Because as I've said, the outer will be more stressed compared to the inner. Okay, so 2 bolt circles will not subject to the allowable shear stress 60 megapascal at the same time, because the shear stress due to torsion increases with its radial distance. Okay, so recall that, okay, we derived actually this one. This is where we derived a while ago the P and R relationship. Okay, so this one, we started from your lambda over R1. Okay, so this is what we are using. So tau 1, shear stress on the first bolt circle over G and then R of that first bolt circle is equal to only or proportional to the second bolt. But since G, okay, G there is the modulus of rigidity, and that is constant since we are talking about the same type of bolt. Okay, the same material in the bolt. So you can cancel that out, then you are left with tau over R1. So they are proportional. So this is what we will be using to establish, since if we will try to maximize for us to know the capacity of the coupling, then you should know which one we will be putting, or we will be using the entire 60 megapascal. Okay, as I've said, outer is more stressed. So by observation, you can say that I should use that 60 to the outer. But the question, how will I solve? How will I know the smaller value that I will be using for the inner circle? Okay, so this is what we will be using. Okay, so but in case you do not know which one is more stressed, all you need to do is assume. Okay, let's say if the tau 2, I will make that one the first, the inner circle, I will make that one the 60. Okay, if I will do that using this derivation that we did, 60 is to 150, that's the radius of the inner. So tau 1, that is the unknown, over the radius of the outer. So play around with that, your tau 1 will be 80. So if I will maximize the 60 in your inside circle, then the stress in the outer is 80, which is not possible because that will fail. We can only attain up to 60. Okay, that is the maximum. Therefore, that will fail. Therefore, that is wrong. The inside will not be the one to maximize the 60. Rather, I will check that one using the T1. But as I've said, you can actually by observation. You can actually decide by observation. The outer is more stressed, so use that as the maximum. Okay. But however, I will show you. So as I've showed you here, you cannot do that in the inner. So I will put that on the outer. So if T1 is at 60, then T2 will be 45, which is correct. Because the farther you will go from the center, the stress will be bigger. So the first or the outer is 60, the inner will be just 45. it is not 60. It is wrong for you to say that all of these are 60. That is violating the idea of a torsion that is a variable stress. Okay. So, this is what we will be using, not this. So, the outer is 60, the inner is 45. Okay. So, what does that mean? If that is the case, then if we will try to exceed the capacity of the coupling, what will fail first is the outer bolt. This will fail before the capacity of the inner bolt will be reached. Okay. So this is just the continuation. Okay. So now all we need to do is solution. We already derived your tau. Actually, our purpose here is to find the t. But if you try to look at the formula, if ever we know P1, R1, and so on and so forth, then all we need to do is substitute. However, yes, we know the R1 and N1. We know those ones, R1, R2, N1, N2. But we do not know P. And how are we going to solve P? Is by ratio and proportion, isn't it? If we know one of that. But how will we solve P is, of course, going back to the formula of this torsion, isn't it? Torsion on the coupling. This one, wait lang. This one, what's that? Okay. I will, okay, meron yan sa slide. What's that here? Okay, so, this one, ito. Saan yan? Let's find. The one we derived a while ago. This, okay, I forgot that is the previous slide. Okay, so this is your P, area times tau. So, again, we are after T. So, T is the PRN1, PRN2. But we do not know P. How are we going to solve that? Is knowing the area, but we should know the stress on that bolt. Okay, so that is what we are trying to figure out first, the stress on the bolt, before we will solve the P handled by the bolt. So, continuing in here, so we already know the outer, which is 60, inner to be 45 on the tau. Okay, so PRN, break this down into area of the circle, tau 1, area of the circle, tau 2. So, you know your D1, D2, substitute that one, but your tau 1 is, again, that is the outer, that is 60. So, I will input there 60 megapascal. Tau 2 is just 45. Okay, it is wrong for you to make this one equal. It is very, very wrong. So now, calculate, okay. This is the one being handled. If you will calculate the value of this is the one being handled by your outer, and then this is the one being handled by the inner circle. So summate this one, that will give us 10720.68 Newton meter, or making that kilonewton divided by 1000, 10.72 kilonewton meter. So that is the capacity. Okay, that is the capacity of our flange bolt coupling with two circular bolt arrangement. Okay, this is for one circular bolt arrangement. As simple as that. But for more than one circular bolt bolt circles, then you should have there the ratio and proportion, knowing that the stress increases as you go outwards. Okay, as you go outwards from the center. So that's it for flange bolt couplings. So let's review some concepts. Okay, flange bolt couplings are an example of application of torque. Okay, so we can actually now consider this as a design. So if ever you are now having there a member, two members, you are going to connect that one, but the problem is how you are going to transfer the torque on this member on the other side totally. Okay, how are you going to transfer that by means of connection? Then we need to design the connection. And then how are we going to connect the ends? By means of a flange and bolt. So of course, assuming that the flange is strong enough, then what we will try to worry about is the bolt that will be connecting these two flange. So this is an actual application of torque. Okay, shearing stress caused by torsion. Okay, so what else? One more thing, this is again important, is to increase the torque capacity of a coupling, one can either increase the number of bolts and add additional bolt circle, or choose a material with a higher shear strength of the connecting bolts. So in case you will try to maximize the outer the outer bolt circle, and it seems that the bolts are very, very close, then maybe you will create another bolt circle which is smaller. But still, if those still cannot handle the torque, then maybe you need to adjust. Okay, you need to adjust the sizes of the bolts, or you need to add more bolts. But still, if that is not enough, then your last choice there is to adjust the strength of the bolt. If you say adjust, I mean is choose a higher strength material as a bolt. Okay, so that is a concept on actual designing of flange bolt couplings. So if you have any question, we will discuss that one in the live meetings, or you can comment that one below the video. So thank you very much for watching.